Hi, my name is Schwerdtner, and in the next 15 minutes, we're exploring a new method for structure-preserving model order reduction based on parameter optimization. The key point I want to make today is that for structure-preserving model order reduction, directly optimizing the reduced order model parameters instead of obtaining them via subspace projection is a good option to get a highly accurate reduced order model. As an illustration, consider these two curves showing the approximation error obtained when using either balanced truncation, Beattie, or IRCA, the iterative rational Krylov algorithm, to compute an approximate small-scale model for a given large-scale port-Hamiltonian model. I'll explain what port-Hamiltonian means in just a second. This error decreases rapidly as we increase the size of our reduced order model, since we can then capture more of the full-order model's dynamics. However, neither balanced truncation nor IRCA generically preserve the structure of our system. This means that our reduced order model is not necessarily port-Hamiltonian like the given model. But for some applications, model structure is essential, which is why research has been conducted to adapt balanced truncation and IRCA to also preserve that property. But with these adaptations, as you can see, the accuracy for the same reduced model order R is worse up to a few orders of magnitude. When I first looked at that plot, I asked myself, is it impossible to construct structured approximations as accurate as unstructured ones, or do we just not find them with these two methods? The answer is, it is indeed possible, and in this talk, I'll explain our method which can be used to find structured reduced order models which are just as accurate or even slightly more accurate than the unstructured reduced order models obtained with the original balanced truncation or IRCA. Today, we only consider the port-Hamiltonian model structure, but the method that Matthias Voigt and I came up with is applicable in a much broader setting. After a brief description of the port-Hamiltonian model class, we will review structure-preserving adaptations of balanced truncation and IRCA, and after that explain our new methodology, which consists of first determining a complete parametrization of the considered system class, and then optimizing this parametrization. Let's describe our setting. At first sight, we have a linear dynamical system with input u, output y, and a state x. A closer look reveals that our system and output matrices look a bit unusual. They are constructed from several matrices that must satisfy the following constraints. J must be skew-symmetric, while R and Q must be symmetric, positive, semi-definite. Only B can have arbitrary elements. So that's our port-Hamiltonian system, and furthermore, since we do model order reduction, our state dimension n is much larger than the input and output dimensions m. Therefore, we must find a small system sigma tilde, such that when we use the same input u on both systems, the respective outputs y and y tilde are similar, so the output error E is small. For linear systems, we have that nice error bound we get from comparing the transfer functions h and h tilde of the original and the reduced model respectively. Now the entire change from regular model order reduction to structure-preserving model order reduction is that now our reduced system is constrained to also have the given structure. The error bound is still valid, so it is still our goal to minimize the difference of these two transfer functions, for example, with respect to the h-infinity norm, to get a good approximation. Let's find out how this is achieved in the port-Hamiltonian version of balanced truncation. Here we start with our given large-scale system, compute the ordinary balancing transformation which can be used to rewrite the system in balanced coordinates, such that now the dynamic is mostly captured by the first few states. This transformation preserves the port-Hamiltonian property of that system, as it just leads to congruence transformations of our constrained matrices. However, in contrast to ordinary balanced truncation, now we cannot just take the upper left blocks of these matrices, as this would destroy the structure. Instead, we have to take the Schur complement when reducing our Q matrix. But with that minor adaptation, we obtain a balancing-based port-Hamiltonian model by then taking the upper left blocks of the remaining matrices J, R, and B. On the other hand, IRCA is based entirely on tangential interpolation of the transfer function of the given system. Tall and skinny projection matrices V and W are computed such that H tilde, our reduced transfer function, has a tangential Hermite interpolation property at optimal points Si. This means that at these points, in certain tangential directions Ci and Bi, the transfer functions and their respective derivatives match. These optimal points are not known beforehand, but IRCA tends to converge to them by means of a fixed point iteration. Now the problem is that the reduced order model is only port-Hamiltonian for a very special choice of W. Therefore, in our setting, we cannot use it anymore to give us the interpolation property. The solution proposed in the literature is to give up matching the first derivative but proceed with the same iteration rules as in conventional IRCA. To check the performance of these methods, let me introduce you to our benchmark system for today. It's a classic mass spring damper chain with force actuation and velocity measurement at the first two masses. The constants are chosen such that we have this nice and smooth transfer function, which should be easy to reduce. But if we look at the frequency-wise error for increasing reduced model orders, we can see that it does not really decrease. So the large H-infinity error we saw in the beginning was not due to just one single unfortunate peak, but the approximation quality is bad over a wide frequency range. To find a different path for us to take, let us reflect upon the currently dominant way to compute reduced order models. Starting from a given large model, we try to identify subspaces in which most of the dynamic happens, project the system matrices into that subspace, and obtain our small model. And if we need to preserve some extra structural property, we just adapt the projection. However, with that special projection, we may lose optimality or error bound guarantees that the original subspaces gave us. Therefore, I propose to focus less on the subspaces, but more on the reduced order model, because that is what we're really after. So let's find a more direct way from structured full order model to structured reduced order model and try to minimize the approximation error on the way. To parametrize a dynamical system, we just turn the system matrices into matrix-valued functions. Then we need to take care that we satisfy the structural constraints I told you about in the beginning, the skew symmetry and the positive semi-definiteness. But with a function VTU, which maps a vector onto the upper triangular part of a matrix, we can easily express both skew symmetric matrices by subtraction, and also positive semi-definite matrices can be constructed via multiplication. The B matrix is not constrained anyway, so a simple reshape operation does the trick here. The optimization part is a bit more tricky. The first idea to try is naturally a direct optimization of the H-infinity error. For that, you can first compute the current H-infinity error, for example using Lenorm subspace, our H-infinity norm computation engine for large-scale systems. This also gives you the point where the H-infinity norm is attained. With that, you can compute the gradient of the H-infinity norm with respect to our parameter vector theta. Now, you have value and gradient and can simply push this into a nonlinear optimization solver. Since it is a non-smooth and non-convex problem, we use Granzo, which is Tim Mitchell's tool for exactly this kind of problem. In the current slide, you can see the H-infinity error that's resulting from applying this direct H-infinity norm minimization method depicted in orange. Unfortunately, after a really promising start, the error does not decrease for reduced model orders larger than 8 and instead returns to the larger errors of the previous methods. To explain this behavior, I have prepared a little demo that I want to show you now. So I built this model of the error of a transfer function. The frequency is indicated on the horizontal axis and the error is shown on the vertical axis. Now, what you need to do when you minimize the H-infinity norm of that error transfer function is you first need to find where the highest peak is attained, and then you vary, or the optimizer varies, the parameters such that this peak is pushed down a bit. Right, next iteration, we again need to find the highest peak and then push that down even further by varying the parameters. But now very quickly we run into the situation where there's a tie between several peaks that are all around the highest peak. And now this tie is then broken arbitrarily, and then sometimes we push this peak down and at other times we push the other peak down. However, that's just a non-smoothness, and non-smooth optimization engine should be able to take care of that. However, convergence is slowed down dramatically. And as we push down these peaks, more and more peaks enter this tie of being the highest peak, and we need to sort of take care of all of them on the way down, and more of them basically. And so it gets harder and harder to find a good descent direction. And also each time you do a computation of the H-infinity norm, so you evaluate the value function, you only get tiny bits of information because you only get the the gradient at one of these peaks. You don't really get a joint gradient to push everything down by the evaluation of the value function, which is the H infinity norm in this case. And that's not really what you want to do. So what you want to do instead is find a way to push all peaks down at the same time, right? And have them at the same low level, and also to have your gradient contain information on all the peaks by evaluating another value function. And that's what we're going to look at now. So how can we do exactly that? How can we push the error at multiple frequencies to the same low level? For that, consider our new loss function L. It takes a positive real value gamma, the given transfer function, our parameterized low-order transfer function, and a set of sampling points on the imaginary axis. To compute the loss, the norm of the difference between the given and our parameterized transfer function is computed only at these sampling points. We then subtract a threshold value gamma from that norm. Now, only if that difference is larger than 0, that is, only if the norm of the error is larger than gamma, we square that difference and add it to our sum. All samples at which the error is smaller than our threshold gamma are ignored. Using this loss function comes with several benefits. There is no need to compute any H infinity norms, which is computationally demanding. Furthermore, our gradient now contains information on the error at all samples where the error is too large, so we don't just focus on a single peak, but a broad range of frequencies at each optimization step. Finally, we can set our threshold gamma to get the approximation quality we need for our use case. We can also iteratively reduce it between runs of our optimization solver to get a reduced order model as accurate as possible. We now look at the algorithm we've constructed around this loss function. It takes as input the given large-scale model, or rather its transfer function, a pre-initialized parameterized low-order model of the desired structure, and the set of sampling points chosen by the user. Here we've just used logarithmically spaced points on the imaginary axis. With that input and an initial value for gamma, we can compute the loss and minimize it by optimizing the parameters of the low-order model. After the optimization, we check if our optimal function value is 0. If that is the case, then we know that at all sampling points, the error between the given and reduced transfer function is less than gamma. Then we can select a smaller value for gamma and restart the optimization. As initial value for the parameterization, we can take the previous optimizer. We can repeat that process until our required accuracy is attained, or keep going until the optimization breaks down with a loss value larger than 0. Then we know that our currently requested accuracy cannot be reached and the algorithm terminates. So let's check the results. The errors obtained from our method are shown in green. For the computation of each reduced order model, we reduced gamma as much as possible. That means we only stopped decreasing it after the optimization could not determine any parametrization for which the error at all samples was smaller than gamma. As we increase the reduced model order, the error drops significantly also for higher reduced model orders, so it seems less likely that we get stuck at a local minimum. Notice that there are quite some peaks that need to be handled at the final reduced orders, and how they all have similar maxima. This highlights the well-suitedness of our loss function for the particular use case. We can summarize the previous error curves in the following H-infinity comparison, which reveals that our method leads to H-infinity errors up to 3 orders of magnitudes below the error that is resulting from using the other methods. We can also compare the H2 errors, which show a similar behavior. In summary, we've computed highly accurate structured reduced order models by directly optimizing the entries of the reduced order model system matrices. The crucial point that made this work was the use of a loss function that captured the error more globally than just the H-infinity norm. I'm currently looking at additional model structures where I can apply this framework. Furthermore, I'm developing a method that automatically selects the sampling points to release this responsibility from the user and decrease the computation time. With that, I want to thank you for your attention. If you have questions or remarks, I'd be happy to discuss them with you. Finally, I've made a one-page PDF summary for this talk with a reference to the corresponding preprint. It is available within the conference tool. If you have trouble finding it, just contact me at schwert@math.tu-berlin.de, and I'm happy to email it to you.